All right. So we've talked about deadlocks as a problem that happens because we have multiple users, many processes, and we have limited resources, and usually they are dedicated, and there's more than one process, and these resources are not shareable. I mean, it's mutually exclusive. These are the conditions of a deadlock. And if we cannot take a resource back from a process until it gives it up, that's non-preemption. And if we allow a process to hold a resource and needing another resource that's not available, goes waiting while holding the first resource, that's hold and wait. And then if we end up having a circular wait, if the four conditions are satisfied in a system or happen in a system, that means we're going to have a deadlock. So anytime our system has multiple processes, there is a probability that a deadlock is going to happen if those four conditions are in the system. So now we're going to look at another problem or another issue that occurs in systems, computing systems and other systems, due to multiple processes running simultaneously. Nothing to do with deadlock, but it's quite similar, and you need to stay with me. This is called critical sections, critical regions, or critical sections. First, you need to know something called threads. We have processes, we have programs, processes, and threads. Anybody knows the difference between a program and a process? What is the difference between a process and a thread? Hands up. Yeah? Sorry, we are asking about processes and programs, sorry. And then we get to thread, sorry. Yeah, so a program is any list of instructions that's static, stored somewhere. It's not running now. That's called a program. If we start executing it, we call it a process. Now, you can have many processes running simultaneously. The operating system will protect every process from other processes. They're not allowed to talk or communicate together. They're not allowed to access. They can communicate, but indirectly. Like one of them can write to send information to a file, and the other one reads from that file. But that's writing to a file is a slow process, especially if a file is on a tape or a hard disk. It's a mechanical device, it's very slow. Remember, inside the CPU or inside main memory, information almost moves at the speed of light, almost at the speed of light. Hard disk is a mechanical device. It's really, really slow in relative terms. So, threading is another technique of execution. And a thread is you take a process, it's like you put it in memory, it starts executing, and you can say, okay, make another copy of this process, right onto itself. So in memory, it doesn't take any more space, it's the same code. But now it starts running again as an individual separate process. So it's two processes executing the same code. This is just like if you have, say, in a kitchen and you hung up a list of how to make some meal, how to cook something, recipe. So that's a program. and one chef goes in and start executing line 1, line 2, line 3. And then a few minutes later, or 10 minutes later, another chef walks in and start executing. So now we have 2 threads running at the same time, but they're executing the same code. This is exactly what the idea of threads. You put the code once in memory, and you can have 10 separate processes executing it. But we call them threads. So threads, some refer to them as child. A thread is a child of a process. So you have a process, it can generate many threads. That means baby processes running, executing the same code. Which one is better, running separate 10 processes, individual separate processes, or running one process that can create 10 threads? Threads are better. They're more efficient. They only use the same code in memory, while 10 processes, each one of them will need its own code in memory. So memory is a lot less if you are using threads. You only need enough memory to hold one code, one copy of the code, and the others are really executing. It's like you have one kitchen, but you have 5 chefs, 5 people cooking the same recipe. And they might be doing different parts of it. And sometimes they even execute the same step. So threads, guys, are much better, more efficient at memory. And remember, when we do context switching, we change one process to the next process, takes a bit of time. With threads, from one thread to another, it's a lot quicker. The context is quicker because we don't have to change it. It's pretty much the same code. But still, they're individual kind of threads running. So they have shorter context switching or quicker. They are better at memory. And what's the most important thing is that they both use the same code and the same variable. So if one of them has an array, puts a number in an array, the other one can go to that array and read that number at the speed of light. So this is the main advantage. Threads can communicate and exchange information. They're like individual processes, but they can talk with their other siblings at such tremendous speed. So instead of you writing 2 or 3 processes that you need them to talk to one another, and the only way processes, well, the most used technique for processes to talk, if I have a program, you have a program, we want them to communicate. One of them, my program will generate data, write it to a file on the hard disk, and you open the file, read that information. That's how we keep sharing information. Processes share information, but that's very slow. If we wanted to exchange information immediately at fantastic speed, well, then don't run them as separate processes. Put the 2 processes in one program, upload it, and then in there say, threads, give me 2 threads. One will run the first part of the program, one will run the second part, and they will be able to exchange information. They are almost there. We look at them as one process, though in fact they're different threads or different. It's like, again, the 3 or 4 chefs in the same kitchen cooking the same meal. Each one of them is cooking its own meal, but it's the same meal. They're all following the same code. Okay, so threads is, hopefully you will get to start to do some programming using the technique that's called threading. That means you run a program and inside you split it into 2 threads and say the first thread, if you're the first thread, do this function, and if you're thread number 2, do this function. The only difference between threads is their ID. That's all. Thread number 1, thread number 2, thread number 3, but they all have access to the same code, they all have access to the same data and the same variables. And it's a very good technique for programming. So, and they call this parallel programming. That means you have 2 or 3 processes running simultaneously, really simultaneously. And most of the time there's no issues, but sometimes there are. Sometimes parts of that code cannot be executed simultaneously. You can run most of it, even simultaneously. You can do the same. Like if you have two chefs, and one of them say beat the eggs, and the other one, they can both beat the eggs separately if they have separate, whatever, mixers. But they're part of the thing. Maybe there's only one oven, and one needs to maybe turn the grill up, and this guy is a little bit early, put it there, and the other guy turned the grill, so they might ruin each other's cooking. So there are some parts of that code we say it's critical. You should not do it at the same time. All right, so that's what I'll talk about today, and the next lecture is critical regions. We call them critical regions. That only happens if we have threads running, if we have parallel processes executing the same code. Any questions so far? So it's slightly different to deadlocks. We know what deadlocks is. And deadlocks, it's an entanglement of processes requesting resources and waiting, and they get stuck together. Some books call it the deadly embrace. That means this process is asleep, we're needing that, holding one resource and needing another resource. Another process has this resource and pointing at another resource. And one of them, the last one, is looking for the resource that's held by the first one, and so on. So that's a deadlock. We know what a deadlock is. And it never happens to one process alone. If one process alone does not finish, does not get a resource, what do we call that? If a process, one single process in a system, doesn't finish for an hour or 2 hours or a day, we don't call it a deadlock. A deadlock needs more than one process, at least two. One is causing the other one not to finish. Each one of them is causing the other to wait. If it only happens to one process, we call it starvation. It's the main difference between starvation and deadlocks. A deadlock involves more than one process, two or more. And it involves circular weight and involves non-shareable resources. Any questions, guys? So let's get into the topic. All right, so we'll talk about parallel processing. We'll talk about parallel processing when two or more processors operate in unison. So now also we can talk about systems that have two CPUs and they run at the same time. Processor manager needs to coordinate the activity between these processors. And the processor manager needs to synchronize the interaction among the CPUs. Multi-programming, guys, is when several programs are running at the same time on a single processor. Somebody might ask you, so what's the difference between multi-programming, that means many programs are running, or multi-processing? I think maybe the easiest way to think of it is to think of the processing is the processor. We have many processors executing many programs simultaneously. Multi-programming, lots of programs, but there's one CPU. And we have to keep switching that CPU between them. Why do we need parallel processing? We have better throughput. If we have 4 CPUs, that means we can do more work at the same time and increases computing power. The advantages: increased reliability. Sometimes one CPU breaks down, the other will continue working. and faster processing. We can get the CPUs to execute the same program. One program. Instead of every CPU runs a program, we can have a program, split it into two parts, and let two CPUs run it. And sometimes you get to one line of code, split it between multiple processors simultaneously. So just briefly looking at the hardware aspect of it, even though it's not, our main task here, but how could you have many CPUs running on a machine, one single machine? There are three approaches to designing those. Either a master slave, like we have one CPU in charge and a few other CPUs that listen to the main CPU, or loosely coupled or symmetric. Symmetric, that means they are equal. Each CPU has the same responsibility as the other CPUs. So the master one, there are three approaches. It's an asymmetric, that means they're not equal. On both sides are not the same. There's one that's the master and the other CPUs that will do the work. They do not control. The master processor is responsible for managing the entire system. So there's one CPU, takes receives all requests from everybody, and say, okay, I have 4 working for me. You do this program, you do this, so it spreads. It basically just schedules everything. It manages the entire system, maintains status of all processes, so it keeps an idea of all processes that are executing, performs storage and input and output, scheduling the work for other processors, and executing all controls. So the master said you really have one CPU doing all the work, scheduling at least, and dividing the work between the CPUs. The other CPUs, they don't care about that, they just run execute the instructions. Give me any instructions, I'll run them. So there's only one CPU that's in charge. It's easy maybe to do, but it doesn't give the best efficiency. Sometimes there's lots of queues waiting because there's only one CPU managing everything, especially when the system gets bigger. So that's what the master CPU design of a system. Master CPU has 2 other slave CPUs, so it gets all the demands, all the requests comes to the master, so you run this, you run this. When you write it for information, it controls all input and output. Otherwise, there'll be chaos. But it's not really the best system, as I said. It's easy to implement, okay, so that's the advantage, but disadvantage, the master processor gets overwhelmed. It's simple, that's the advantage, but the disadvantage, reliability is not great. When you have lots of CPU working, you say, okay, so if one stops, the other will work. No, if the master stops, that's it. Nothing will replace it. So there's no reliability, and can lead to poor use of resources and increases the number of interrupts because they're all going to the same processor. The next system is called the loosely coupled configuration. Every CPU is kind of independent. It has its own copy of the operating system, and once given a job, it remains with the same processor. So it's like, this is almost like you have 3 laptops, one on top of the other. They're almost independent of one another, almost. There's very little communication between the CPUs. If you submit, each one has its own main memory, and each one has its own input and output devices. It's easy to manage. Everyone has its own I/O. So they don't interact, but it's like we have 3 computers, separate computers, almost. Very little interaction between the CPUs. This is called the loosely coupled. They're connected together, but very loosely, very little. So you can read this about it. Once allocated, if you give a job to one process, you cannot share it with the others. So if you have 3 programs, you send to each program to one CPU. Each one does its own scheduling, and if one of them fails, the others can continue working. But this is basically, you don't get a lot of advantages for having multiple, you can have them, might as well have them 3 separate computers, but they still work. This probably might be the better solution, and this is called the symmetric configuration. Processor scheduling is decentralized, and each processor is of the same time. This is more reliable. They're all equal kind, and they use the resources effectively. So basically, they share all input-output devices, and they share memory, and they work together. Now, even a program in memory, we might split it into 2 parts or 3 parts, give this CPU one part and this CPU another part. So the same program or process may be split. Sometimes one single line, like if you have a mathematical operation, you can split it into a few parts and give each processor to do one part of it, so you get much faster, much better execution. All processes must be well synchronized to avoid race and deadlocks. Any given job or task may be executed by several different processors during its run, and more complex as several processors try to access the same resource at the same time. It has more challenging to keep the input-output devices and memory kind of between those 3 processors. For a successful processes synchronization, the resources must be locked from other processes. So the locking technique, we talked about locking technique in the past to prevent a race problem. Remember, you want to read from a file, another process wants to read from a file, you might end up with the wrong results and write to a file. So locking is used, and awaiting is allowed also to happen. So we have locking, and consequently we have waiting. And that's sometimes the start of a deadlock, not necessarily a deadlock. A mistake could leave a job waiting indefinitely, or if it's a key resource, it can cause a deadlock. So we have another problem. Apart from deadlock, we have another problem. We call the critical regions. So if you have multiprocessing in a system, we can have deadlocks. That's one major problem. We can have race problems. We know how to solve race problems with a lock. We can have deadlocks. How do we prevent a deadlock in a system? Any idea how we can prevent a deadlock in a system? If we can eliminate one of the conditions, one of the 4 conditions that are required for a deadlock, if we can remove one of them, then that's it. We'll never have a deadlock. Very good. Now we have something called critical region, another problem. And this is problem of synchronization. A part of the critical region, what's the critical region or critical section? Remember, now we're going to be running the same code. As I said earlier, if we have threads, we have one code in memory. There are multiple threads running it. Little processes, that's not the real term, but baby processes, we call them threads. The same process itself can generate many smaller processes, or not necessarily smaller, it could be exactly the same copy of the same code, but now the only difference between them is the ID. It's like in a family, They're all supposed to use the house, all the full house, TV rooms, that's shareable room, toilets, they're not shareable, kitchen, maybe semi-shareable. And the family have children and children and children, and these are the threads. And also the threads can use the resources in the house. But sometimes there's a conflict happens in the house. Some parts of the resources, some of the resources, really they need to be synchronized in order to be used, because they are not shareable and they can cause problem. So critical region, what is, if you're asked what is a critical region, and I was asking earlier on, what is a deadlock? A critical region is a part of a program that must complete execution before other processes can have access to the resource being used. So if you have two processes running the same code, I'm going to have a process here running the code, this line here, one line at a time on this side, another process running it here at the same time. It's no problem if running the same lines, the same instructions, but some instructions, they must not be run simultaneously. Some parts of the code, maybe 3 or 4 lines here, if two processes run them simultaneously, they're going to destroy. They're going to be a problem. Just like we talked about 2 chefs walk into the kitchen and they can both work simultaneously, prepare the same meal. But when you put that cake under the grill, one of them doesn't want it under the grill, but the other one does. Oh, that can cause a problem. So maybe some parts of the code cannot be executed simultaneously. We call that part of code, we call it critical code or critical region. So remember, with deadlocks, we're talking about the resource. Is this shareable or dedicated? With critical region, we're not talking about the resource, we're talking about the code itself, the program instructions. So processes within a critical region cannot be interleaved without threatening the integrity of the operation. So if we have 2 processes go into the critical region, they will threaten that they can cause problem in the system, whatever the problem is. This is like a critical region. These 2 guys are going for a walk. In the whole park, it's fine. They can walk anywhere they like. But there's some parts, this part of the park, it's so critical. They should not use it simultaneously. And that way, if they get stuck there, and if none of them decides to release or walk back, then there could be a problem. There could be a conflict. So that's in the code that we write most of the time. We can have many users executing the same code. And they can execute even the same line. But there are some lines of code, no, they cannot be executed simultaneously by more than 1 user. You can think of this as part of the code. This part cannot be run by 2 processes or more, only 1 process. We call this critical region. And therefore, you as a programmer, you need to protect that part of code. It's like you're designing a park, and then you come to this part where only 1 user should go in. You should stick a sign, say, okay, hold on, make sure there's nobody there before you start moving. Cars as well. Sometimes you have a road that's going around, and then there's a bridge, and that bridge will only take 1 car. So sometimes we call that a critical section if 2 cars cannot go in the opposite directions. So some control needs to be applied there. It's just to see, so you understand what the critical region is. The rest of the road is shareable. It's like the rest of your code and your program can be executed by 3 or 4 processes at the same time, but not that little part there that we call the critical region. So this is now what we're going to be talking about, how to control the critical region, how to overcome the problem. What is it and how is it sorted out? So so how do we control it? By allowing somebody to go on the other person and say, no, you have to wait. You can't go in there. This is called synchronization. Synchronization is timing. You cannot simultaneously at the same time you go into that part. We're going to hold, like we're going to delay you a little bit. So there's time. And anytime you hear the word synchronization, it's strongly related to timing. So synchronization is something that's implemented as a lock and key arrangement. We've already used that. So we put a lock on somebody, they cannot go in, we let the other one go in, and when they finish and clear, we unlock this and they can get moving. So the process must first see if the key is available, or the resource is available, and if it's available, the process must pick it up and put it in the lock to make it unavailable to all other processes. And there are three mechanisms, three techniques, and you need to understand each one of them. So 3 ways, 3 techniques to protect critical regions, to protect against the problems that can happen in critical regions. The older technique, and it's no longer used, called test and set. And next, these 2 are modern ones. One is called the wait and signal. The other one is almost the same as wait and signal, but it's more general kind. You can apply it to multiple cases. How does it work? This is the first one. How it started. But this is almost the same idea. It started with the train. The train companies, 100 years ago, trains started, or even longer. But in the train network, you have tracks, and it's expensive to build tracks, and therefore there are parts that are shared. And when we are running multiple trains, that part that's shared can be a source of danger. And that's what now we refer to it as the critical region. This part here of the train in the middle, where if 2 trains approach from 2 different directions and they cannot see each other or one another, they can end up colliding in the middle of the critical region. And by the time they see each other, it's too late to stop. And many trains collided on shared tracks, and that's the critical region. So of course, train companies solve that problem by sticking those signals. And these signals are supposed to indicate whether the critical section is free or is it somebody's using it now. And if somebody's using it, they want the train to stop, approaching train to stop until the critical region is free. In the older days, they use those handles. So the handle goes up in front of the train, that means stop, and if it goes down, that means you can go, clear to go. And then red and green lights were introduced. It happens, this can be, an issue in so many other ways. So the way it operates, a train approaching a critical region is like your program, you're writing your code and this process is going. And now we know there's a critical region in the middle. So what do you do? Or what does a train do? So they put a light or the handle or the semaphore, but for now just let's say red light. If there's some train here, well then the red light will come on in this side to tell them don't move. And then when the region is clear, then it's switched to green. So just put in the algorithm for it. Simply imagine this is the critical section here. These are part of the same code, but imagine a train driver is coming in here. So it's approaching. Now it's just about moving from the top, going down, executing. Now we get to this point. You'll have to check and you look at the light. And if the light is red, that means the critical region is busy. You have to wait. So you stay waiting here. Don't go any further. As long as the light is red, you stop. So you just keep checking, looking at the light. It's just like coming to a crossroad in a car, driving a car. You come to a crossroad. That's critical section. You get through green or red light, that means you have to stop. And you have to keep checking it, until it changes green. Who's going to turn it green? The other guy that comes out, remember there are two using that critical section. So the other train, when it comes out of the critical region, it will turn it to off, so it will switch off the light, turn it into green, and now this guy, the next time it sees the green one, it goes into the critical section. So the idea is simple, but there's one light, there should be one light, one flag that works by both, and one of them will switch it on. That means the critical section is busy, and the other one switch it off, or the same person when they finish. This is again, it's like the toilet in an airplane. The airplane itself is shareable resource. Many users use it, but part of that airplane is not shareable. Let's say the toilet. So if somebody go into the toilet, if they see the light that it's busy, that means if they see the signal that say that's occupied, then you have to wait. The user in the airplane toilet, when they finish and they switch the light off or they turn the signal that says busy off, then another user can go in and switch it on and use it. And that's kind of, it makes it only shared by one user, or used by one user. So it reduces the conflict. Sometimes, so this technique is known as a test and set. You test it and set it. Like two train drivers coming in from two different directions. The problem with this system, guys, if two approach at the same time, and the two of them, they check that light at the same time, and they see it off or green, and they say, oh, there's nobody in there. And the two of them at the same time go in there and switch it on. So they switch it on and say, I'm in the critical section now. They both hit that switch at the same time. Now, each one of them thinks, and just after switching the switch, each one of them thinks they did switch the light simultaneously, because they've done it simultaneously. And they both go in there thinking, I'm happy, I'm the only one in there, and in fact they're not. And that's when the crash happens. So this checking the light first, looking at the light, is it on or off? They say it's off. Okay, Tom, switch it on. I'm talking to my assistant here. My assistant switches it on. And then we go in. That's not good. Why? Because maybe at the other end, another user came in at the other end and they looked at the light and it was off. And at the same time, they hit the switch and turned it on. And they go in as well. So that's the problem that used to happen with trains. Trains come in from two directions and both of them look at the lights and they say, oh, it's green, there's nobody there. And both of them decide to turn the light. See, this is the situation that used to happen to trains. Remember, trains cannot see one another, but they can both see the light. This light is green, is on either side. It's the same light, comes on. So they both approach They both see the green light. That means there's nobody in the track. They both hit the lever here. There's a switch there, the lever beside the train. So the train driver hits that lever and turns the light red. And they both start moving. Each one of them thinks, oh, I'm after turning the light red. I booked it and I'm going in. But they've done it exactly at the same time and they end up crashing. Most of the time, they don't do it exactly at the same time. There's always somebody does it 1 minute or 1 second before the other. But that was the problem. He's looking at the light first, checking it, and then switching it on. Those 2 steps, they should not have been interrupted. Looking at the light, looking at the flag to see it's free, and then turn it on to indicate it's busy. These are 2 steps, but they are interrupted. Just like what happens in the race problem. You check and I check. We get the balance, you get the balance. I update it, write it. You update and write. So they said, no, it doesn't work that way. That's a problem. So checking and turning must happen at the same time without interruption. So if I'm looking at something and I'm going to turn it, you're not allowed to look at it yet at the same time. It should be hidden from you. Or when I go to look at it, and I also, if it's on, I'll immediately turn it to red. There should be no delay between checking the flag and changing its value. That's really the main part. So in test and set, in computing, we call this test and set. This test and set is one single operation. It's indivisible machine instruction executed in a single machine cycle. So testing, let's say, in computing, we just say x equals 0 or 1. You put 0, check it. If it's 0, turn it to 1 to say I'm going in. If it's 1, then wait, you cannot touch it. So if it's 0 now and 2 programs come in at the same time, they're not allowed each one to look at it. Is it what value is it 0? The other guy says what value is it 0? Turn it into 1. This guy writes 1, and then they go in. They're not allowed to read and wait and then write the 1. Those 2 operations have to happen simultaneously in non-divisible kind of instructions. Those 2 instructions have to happen together. Just like what they did with the locking mechanism, remember, in the race. When you go and read the balance and this guy reads the balance. No, if I'm reading the balance, I'm going to try and put a lock in it so no one else can read it. So the actual key is a single bit in storage location that can contain 0 and 1. And with the threads, they can both see this variable. Let's say variable x. Is it 0 or 1? We start with 0. That means the critical section is free. And anytime you approach it, you want to use it, you first check, is it free? But if it's free, you check if it's free, and if it's free, turn it to 1 immediately, in 1 step. Don't check it first. Yes, it's free. Now send another instruction to turn it on. If it's free, like the toilet of an airplane, once it's free, jump in and lock it immediately before someone else jumps in as well. So those 2 operations, they call them atomic operations. Atomic, that means they happen together, uninterrupted. The actual key is single bit, and a process 1 tests the condition code using the test and set. This is why they call this test and set at the same time. You look at variable. Is it 0 or 1? If it's 0, turn it to 1 immediately. If it's 1, okay, wait. Okay, so that's why they call this test. You test this value, or you look at the light. Is it green? Turn it red immediately. The test and set happens at the same time. So that's the operation we use. And this is the mechanism. They call it test and set. So how does it work? Imagine there are a number of processes are executing this code, and This code is simple, there's no problem, except here we have a critical region. So at the start of the code, you need to have those two lines, while F is not equal to 0. 0 means the critical section is free. That means while it's not 0, that means while it's 1. Okay, stop sending messages if you want to listen to, follow this, or at least send it quick. And just concentrate for the next few minutes, and then you can send all your messages. So if you have a critical section in your code, you need to put a lock. This is just like the toilet in an airplane. You need to have a lock at the start of the operation and release the lock or remove it at the end of the operation so someone else can use it. So at the start, for example, if a user comes in, if a process comes in and it finds that it's free, 0 means it's free, there's nobody there. Turn it into 1 even before you step in. Say, okay, this one is busy now, and you go in. Now, if someone else comes in and finds it 1, they'll have to wait at this line. See, this line says, as long as it's not 0, wait. If it's 0, go in. But before you go in, you have to turn it on, right? So 0 means there's nobody there. 1 means there's one person there. You can look at it this way. It's how to remember it. 0 means free. And you can think of this as the toilet part of an airplane, just to get the logic. But it's code. Two processes can execute this line, but if they come to this line, no, they cannot go in together. Whoever gets the flag turned on, they can go in, and the other one has to wait. Right, so this is how it happens. When we start first, we put the value 0 on the lock. This is the lock from the door to a toilet door. We put 0, or free, or green light, whichever, they all give the same meaning. But I'm computing 0 and 1 is just perfect. 0 means it's free. So when you start, initially, you start with the value, initialized value 0, right? On the line before that, and this is, everybody has access to this variable C. So now a process comes in. Process number 1 is executing on its own. There are other processes running, but they're somewhere else. But this is one of the threads. Executing this line, this line, this line, this line. Wants to go in there. Oh, before you go in there, you must execute those 2 lines. It will check, is C equal 0 or not 0? If it's not 0, we'll continue. If it is 0, if it's not 0, you have to wait. If it's 1, then you have to wait here. Keep going around in this loop. Just go around. So if it's 0, what do? You must turn it to 1. There it is. Here is the first line you need to do. See, that line is right at the edge of this critical code. If it's 0, yes, it's 0. It's like you're asking, is it free? Yes, it's free. Well, then indicate that it's not free. It's not going to be free anymore. I want to use it. So you turn it to 1. And you go in. So that's it. See, this process just turned that block into 1. It's just a variable, a bit sometimes. It was 0, it's free. Now we turn it to 1. That means it's busy, occupied. And the process 1 start executing. Another process comes in. So the other process checks, executes the same 2 lines at the start. Of course, it cannot see it. That's code. You can't see it, everybody. Yeah? But it can execute instructions. So it says, what value is C? Is it 0? The answer is, unfortunately, it's not 0, it's 1. Well, then you go sleep for a little bit and then check it every kind of couple of millionth of a second. It's busy? Yes, go to sleep. Wake up again. Is it free? No, go sleep, come back again. So you keep checking frequently after. It's like exactly what happens when you are on an airplane and you need to go to the toilet. You walk down towards the toilet area and you look at the door and you see it's busy, occupied. And okay, you could start chatting with somebody, you look down the window, and then every now and again you check, it's still busy. You do checking and you go even rest and then look again. And if it's busy, you continue waiting until you see it's free. But in this case, there is someone else coming up. Another process. So this one has been waiting for a while. Process 1 is in the critical section. Process number 3 approaches. Process number 2 just did a check. Just going after through the check and said, is that flag still busy? Yes, it is. Go to sleep. The moment it went to sleep, this process 1 left. So see the critical point here. Process 1 left, and when you leave, you turn the light. That means you back to 0. That means the critical section is now free. Process number 2 should be going in, but still asleep. Go to sleep for a little brief period of time. Process number 3 just arrived. It does a check and finds critical section is free. So it goes in and turns it to busy. So process number 2 just missed its turn. Process number 3 came at the perfect time. 1 left, turn this to green. This guy saw that, oh, it's green, it's free. Let me turn it busy and goes in. So process number 2 just went to sleep, checked and then went to sleep. Now it wakes up again and finds it's still busy. Doesn't know who is in there, but it just missed its turn. And if this keeps happening, that's what we call starvation. Because it can happen to one single process. It's not associated with another one, second one that's holding it. No, everybody can come in, and this guy has just bad timing, and it's not checking this fast enough, and somebody else approaching at the right time, and this guy is not lucky. Number 2 is not lucky here. So this is how it works. It's so simple. So simple. 1 bit. That's all it takes for control. 1 bit. It's just the same as with the aeroplane thing. 1 switch. Sometimes puts the red light on or green light off or something. So it's 1 bit that can control, that can protect a critical section. Only 1 user can go in. And we don't allow 2 users to check at the same time, because we have test and set. It's 1 operation. You test the thing and set it before someone else tests it. Okay, we're not allowed 2 processes come in and test. The first one, the second one test. No. If I go and test, I'll switch it. If it's free, I'll turn it to busy in 1 go. That's a good thing about this test and set. Anybody can see any problem with this system? It works, it protects, it's very cheap. It's 1 bit and 1 instruction before this code, 1 instruction of 2 lines and 1 line at the end. This is exactly, if you forget how it works, think of the toilet in an airplane. You come in, and if it's free, in airplane they always have the right busy or free, or occupied and free. If it's free, I mean it's 0 here, you go in and turn it into 1. That means somebody in there. The signal would say busy. Someone else comes in, they read the signal busy or occupied, they'll wait. If they keep looking through the window and someone else comes in, they can jump the queue. And they came before them. If I leave at a certain time, that guy is not paying attention, and a newcomer can go in and lock themselves in. So any issues or any problems with this system? Any advantages or disadvantages? Can you think of any? Starvation can happen. First problem is starvation. Starvation, that means if this process number 2 is unlucky, next time it sleeps again, another process comes in and gets in before it. And each time it checks and goes to sleep, every time it goes to sleep, if the one in the critical section leaves, a newcomer can jump in. So the one problem, that's not something good. We don't want that in a system. We don't want somebody missing their turns. That's the first problem in this system. This is the first system they used in computing. Any other problem? This problem is, what's this doing? It's going around in this loop. What's this loop saying? Is this critical section free? Is this critical section free? Is it free? It just keeps asking. checking. And while you're checking, while you're asking, you're using CPU. So you're sitting in your place, doing nothing, and you're using resources. You're using the CPU, which is a very important and expensive resource. And you could be sitting there for seconds or even minutes. Why should you be using a resource? What do we call this situation? When you use a resource and you're doing nothing. I gave you an example before. Somebody says to you, right, pick me up at 7 o'clock. You go at 7 o'clock, you're driving, you step outside their house, you don't turn the engine off. It's burning fuel, petrol. And that person takes 10 minutes or 15 minutes. You're waiting, but you are burning resources at the same time. So that's not an efficient way of waiting. What's the best way to wait in computing? Is to go to sleep. Don't keep checking. So in computing, probably told you this before, if you want a resource, you only ask for it once. If it's free, you'll be given that resource. What if it's not free? You go to sleep, and the operating system will wake you up when it becomes free. So that is not done in this test and set. So this continuous checking, it's like that movie that, are we there yet? Are we there yet? Are we there yet? If you're driving a car for a long distance, the kid beside you keeps asking, are we there yet? Are we there yet? Drive you mad. It's better to knock them off. And when we get there, we'll wake them up and say, we are there now. Okay. What do we call that? We call that busy wait. So they have a terminology for that. Busy wait. So if you're waiting for something, but you're wasting resource checking for it. Is it free? Is it available? And that's exactly what test and set does. It has a while loop. So that's a bad programming practice. Never keep checking something. Is C 0? Is it 0? Is it 0? And hopefully you'll check it once and it's not 0. That's not a good way. You should only check it once. If it's 0, that's good. If it's not, ask the operating system to wake you up. So test and set is very simple locking mechanism that controls and protects a critical region. You ask what's a test and set. It's a nice mechanism, very efficient, very small, not efficient, but very simple to operate, very cheap. Only needs one bit to control access to a critical region. But it has two problems. Can you name them? Or one of them? What's the problem with test and set? Anybody was listening to me? What's the problem with test and set? What's this continuous checking? What do we call this? Is this free? Is it free? Is it free? You remember what I just called? Anybody remembers? Busy wait. One problem is called busy wait. That means you're waiting, but you're busy wasting resources. Checking, is this, I'm gonna wait, I'm waiting, but I want to continue, can I continue, no, is this 1, is it 0? You keep checking the same thing, you're using CPU when you're checking. Remember, anytime you say, what value is C? You have to run a couple of instructions to see. CPU will tell you. So you need the CPU. CPU is so important to give to you to be checking hundreds of times or thousands of times, which you're not going to be going anywhere. So that's first problem, is called busy wait. And the second problem, anybody remembers what the second problem this test and set is? That's what's happening to process number 2. It can miss its turn, and it's called starvation. So they fixed it in computing, and they came up with a new technique called not the test and set, that's the same technique. Okay, let's just follow those processes approaching, and then we go to the next technique. So here it is. When we start first, remember, it's important to remember the lock that we use in test and set starts with 0, the initial value, which means The critical section is free. Nobody is there. So we must start with 0. Any process that comes in, checks it. Is it free? Yes, it is. Well, then turn it to 1 and go in. Now another process comes in. Is it free? No, it's not. Well, then go to sleep and wait and test it after a short period of time. And keep doing that. That's the looping. Another process comes in right at the time. Process 1 just finished, leaving, turn the critical section to free. This guy comes and tests it, while this one is just gone into sleep. So process number 3 can actually go in, and process number 2 just missed its turn. And process number 2 doesn't even know that 1 is finished. Now another user is in. It's like you look at the toilet of the airplane, the door is locked. You turn away, the occupier is left, a new person gone in, and you look back again, still the door is locked. You don't know you missed your turn. All right, and then process number 3 leaves. What happens when process 3 leaves? It will turn the flag into free, 0. Now the next time process number 2 comes out of its sleep and looks at that and say, oh, it's free. What does it do first? It turns it to 1, busy, and goes in. So now if another process comes in, will not disturb process number 2 because it already has the lock on. And when it leaves, it turns the lock off. Now, as it's leaving, it must turn that lock off. So another user comes in. So every user going in, they check the lock. If it's free, they turn it on, and as they leave, they turn it off again. Okay, free and busy, 0 and 1. 0 is free. You need to know this mechanism, how it works. You need to be able to explain it or answer questions about it. This is a fantastic mechanism, very simple to do, but it has 2 problems. You remember what those problems are? One of them? Busy wait. What's the other problem with test and set? Starvation. What's starvation? What's meant by starvation?
Starvation, when a process is not executed for a period of time because it's waiting.
Yeah, it can wait, and there's no. Yeah, it might not be starvation. When does it develop into starvation? What do we mean by starvation?
When the process is waiting for resources for so long.
Why would it wait for so long here?
Because it's slow.
Because it's missing its turn. It's not locked, but it's just its timing is wrong. It checks at the wrong time. Starvation happens if a process keeps missing its turn. It's turn to go into the critical section, but it misses it. If it keeps missing it, then that's called starvation. All right. So this is the disadvantage and the problems of test and set. It has 2 problems. One is called starvation, one is called busy wait. You need to remember those and how to solve each one of them.